In this video, we'll look at a question in which you're required to calculate the electric field strength and the electric potential at a point due to a few charges. So this is a question. The question says 4 charges of plus 5 nanocoulombs, plus 8 nanocoulombs, minus 2 nanocoulombs, and minus 6 nanocoulombs are positioned in air at the corners A, B, C, and D of a square of side 10 centimeter as shown. Calculate A, the field strength, and B, the potential at the center of the square. Now, electric field strength is a vector quantity and therefore has both magnitude and direction, right? So, being a vector quantity, we must find the magnitude of the electric field strength at P as well as the direction. Now, electric field strength is defined as the force per unit charge exerted by a field at a point in the field. Now, each of these charges will of course emit an electric field, and the point P will basically be at a point would be where P would be in the proximity of those electric fields. So what we want to do basically, we want to find the resultant field strength due to the field emitted by each of these charges, right? Now we just redraw the diagram. So let's say this is our square. Right? So this is our square, and at the corners of the square we have our 4 charges A, B, C, and D, magnitudes plus 5, plus 8, minus 2, minus 6. So plus 5 nanocoulombs, plus 8 nanocoulombs, minus 2 nanocoulombs, and minus 6 nanocoulombs. And of course, these points are, this is point A, B, C, and D. And we want to find, of course, the electric field strength at the center of the square P. Right? So let's just put back the diagonals. Good. Now this is the center of the square P. Now whenever we want to find the electric field strength at a point due to a few charges, what we must do is we must basically place a small positive test charge, or imagine placing a small positive test charge at that point, and then ask ourselves in which direction will this charge move with respect to the other charges. So if we put a small positive test charge Q at this point here, so let's call it a small positive test charge plus Q. Right? Now we're going to ask ourselves in which direction will this charge move with respect to the charges A, B, C, and D. Now let's look at it alphabetically. So we'll go A, then B, then C, then D. Now this is a small positive test charge plus Q. In which direction will this charge be inclined to move due to the charge at A? Now this charge is positive at A, and so is this one. And of course we know that like charges repel. And because like charges repel, if this charge was free to move due to this charge, it will basically be moving in this direction. So what this tells us is that the field strength at this point P due to this charge A will be in this direction along the diagonal towards C. So we can basically start by labeling this as E subscript PA. So this represents the field strength at P due to the charge at A. Right? Now, since we're dealing with this direction, now let's also examine due to the charge at C, since of course it is going towards C. Now, C is a charge of minus 2 nanocoulombs. What we have here is a small positive test charge plus Q. So once again, we're going to ask ourselves, in which direction will this charge Q at P move with respect to or in relation to the charge at C if it was free to do so? Now this is a negative charge, and of course this is a small positive test charge, and we know that unlike charges attract. And therefore, if this charge that we imagine placing here was free to move, it would basically move towards C. And what that tells us is that the field strength at P due to the charge C will also be acting in this direction, right? So this is the direction that the field strength at the point P due to the charge C would act, and therefore what we can therefore say is that we can add these two, so we get EPA plus EPC. So therefore in this direction the field strength at P due to A and the field strength at P due to C will act, and therefore in this direction the overall field strength is equal to EPA plus EPC, right? Now having done that, now let's examine the charge at B. Now at B we have a charge plus 8 nanocoulombs, and once again this charge of course will tend to repel this small positive test charge Q, and it therefore means that the field strength at P due to the charge at B will be in this direction due to the repulsive force. So we can draw an arrow in that direction, and we can basically label it as the field strength at P due to B, so EPB, right? So therefore the field strength at P due to B will be in this direction. Now we must also examine lastly the charge at D. The charge at D is a minus 6 nanocoulomb charge, which therefore means that if this charge that we imagine there was free to move, it will basically be attracted towards D, and therefore what this means is that the field strength at P due to the charge at D would be also in this direction. So because they're acting in the same direction, we add the field strengths, and therefore this becomes EPB plus EPD. So what we've basically done is to basically show the direction of the field strengths at P due to each of these charges. So the field strength at P due to A and the field strength at P due to C will go in this direction, and so we'll therefore add those two, whereas the field strength at P due to B and the field strength at P due to D will both go in this direction, and once again we add them. Now one property of a square is that the diagonals will of course intersect at right angles. So basically if these two field strengths are acting along the diagonals, then what we have basically is a right angle, and therefore these are perpendicular, and when we find the magnitudes of these field strengths we will then use Pythagoras' theorem to find the overall resultant field strength, right? Now let's look ahead, go ahead into calculating the magnitude of these field strengths. Now as I said before, we defined what electric field strength is and the formula for calculating electric field strength. So let's first of all do to EPA. So we can say that electric field strength, let's start under here. The electric field strength at P due to A, let's call it EPA, is equal to 1 over 4 pi epsilon naught times the charge at A, well the magnitude of the charge at A, divided by the distance r squared. Now if you look at the diagram, basically they ask us to find the field strength at the center. The center P is at a distance r from the vertex D. But of course this is a square, and it therefore means that the distance from the center to any vertex will be the same and be equivalent to r, right? So what we need to do now is to actually find the value of r, or as this formula suggests, we need to find the value of r squared, right? So if we look at the original diagram, this is a square of side 10 centimeters. Now so this of course will be 10 centimeters as well. All of this will be 10 centimeters. Now what we want to do is to find the value of r, or at least to find the value of r squared. Now r is the distance from the center to any vertex of the square. Now looking at this, what we've done here is, what we've seen here is a horizontal dotted line, which therefore meets the side at right angles. This is the center of the square, and if the square is of side 10 centimeters, then this of course is going to be 5 centimeters, and this also is going to be of side 5 centimeters. So r we can therefore find by using Pythagoras' theorem, right? So we can basically say that, let's see, we should jot that. We can say that, well, by Pythagoras' theorem, we can say that r squared is equal to 5 squared plus 5 squared. So r squared is equal to 50 centimeters squared, right? But of course, we're working with SI units, And so therefore we need to convert this from centimeter squared to meter squared. And to do that, we basically divide by 100 square or 10,000. So this is the same thing as 0.005 meters squared. 0.005? No, let me check. 1, 2, 3, 4. Yes, 0.005 meters squared. So therefore, r squared is equal to 0.005 meters squared, or we can write it as 5 times 10 to the minus 3 meters squared. So this is the value of r squared that we'll actually be using in this formula. So as I said, what we really needed was the value of r squared and not necessarily r. So having found the value of r squared, we can now proceed to find the value of the phi strength at P due to each of these charges, and therefore find the resultant phi strength at P. So taking this constant as 9 times 10 to the 9 for simplicity, in many books it is given as 8.99 times 10 to the 9, in some it is rounded to 9. So for simplicity and for ease of calculation, we'll take this value of the constant to be 9 times 10 to the 9. And so the phi strength at P due to A equals 9 times 10 to the 9 times the magnitude of A. So A is a charge of plus 5 nanocoulombs, so this is 5 times 10 to the minus 9 divided by r squared, which is basically 5 times 10 to the minus 3. Right? So this should give us 5 times 10 to the minus 9 times 9 times 10 to the 9. The exponent will cancel, so 9 5s is 45. 45 divided by 5 times 10 to the minus 3. This should give us 9,000 newtons per coulomb. So therefore the phi strength at P due to A would be 9,000 newtons per coulomb. And of course we'll proceed and we'll find the value of EPB, EPC, EPD, and so on. So going ahead, we can say that basically that the phi strength at P due to B is equal to 1 over 4 pi epsilon naught, the magnitude of the charge at B divided by r squared. Right? So whenever we calculate phi strength, we don't actually use the minus sign if the charge is negative. It is just the magnitude of the charge. What we use the sign to do is to basically predict the direction of the phi strength as we did previously. Right? So substituting the values here, then this will give us EPB equals 9 times 10 to the 9 times charge at B, which is 8 nanocoulombs. This is 8 times 10 to the minus 9 divided by r squared, which is basically 5 times 10 to the minus 3. And what does this give us? The 9 times 10 to the 9 and the 8 times 10 to the minus 9 will multiply to give 72. So 72 divided by 5 times 10 to the minus 3, that's going to be 14,400. So 14.4, that will be 72 divided by, right, so this will give us 14,400 newtons per coulomb. Right? We continue. We want to work out the value of the phi strength at P due to C. And this is given by, once again, the formula is 1 over 4 pi epsilon naught times the magnitude of the charge at C divided by r squared. Right? So this gives us 9 times 10 to the 9. Now the charge at C has value minus 2 nanocoulombs, but once again we're dealing with the magnitude only. So this is times 2 times 10 to the minus 9. And this is all over r squared, which is 5 times 10 to the minus 3. Right? So if we should basically compare this to that, the only difference is that we have 8 as opposed to 2. So this should basically be approximately, well, exactly a quarter of that. But if you work it out, 9 2 is 18. 18 divided by 5, that is basically 18 divided by 5, that is 3.6. So this should basically give us 3,600 newtons per coulomb. Right? So 3,600 newtons per coulomb. And lastly, we need to work out the phi strength at P due to D. So we can say that we have space. Let me just draw a line here. So the phi strength at P due to D So that's EPD equals 1 over 4 pi epsilon naught, the magnitude of the charge at D, divided of course by r squared. So EPD is equal to 9 times 10 to the 9 times the value, which is 6 times 10 to the minus 9, all over 5 times 10 to the minus 3, right? So for this one, we see that, well, 6 nines is 54. 54 divided by 5 times 10 to the minus 3. That is basically 10.8. So this would basically be 10,800. Or if we were to compare it to what we have here, we're multiplying by 2 times 10 to the minus 9 as opposed to 6. So this would basically be 3 times this, which is going to give us 10,800 newtons per coulomb, right? So having done that, we've basically found the phi strength at P due to each of these charges. Now what we've seen from our diagram is that certain phi strengths will add. So EPA and EPC will add, and EPB and EPD will also add. So if we were to go ahead and add those, we could say that EPA plus EPC and this would give us, so EPA plus EPC, so this is 9,000 plus 3,600, so this gives us 12,600 newtons per coulomb. And similarly, EPB and EPD will also add, so we see that EPB plus EPD, and this will give us, so EPB is 14,400, and we're going to be adding that to 10,800, so that's 24,400 plus 800, that gives us 25,200 newtons per coulomb, right? Now, having worked out those magnitudes, we're no longer in need of this diagram, so we'll basically erase the diagram and just redraw this little piece which shows these field strengths, perpendicular field strengths. So let me just try to redraw it. So what we have here, and this of course is a right angle, so this is EPB plus EPD, and this is EPA plus EPC. So if this is how the field strengths are acting, then we can actually do this. We can actually complete our parallelogram. So if the field strengths are acting like this, then the resultant field strength, of course, will be somewhere here. All right? So, of course, this will be the same thing as EPB plus EPD. And let's take our angle as theta. Right? So, what we could do, we could basically just redraw and just put in the magnitudes and just use the right angle triangle. So this of course will also be a right angle, right? So let's do that. So what we have is this. And this time we'll just put in the magnitudes. So this would be our resultant field strength. Let's just call it EP. Now EPB plus EPD, we know that is 25,200. So this right here is 25,200. And EPA plus EPC, this is 12,600. Right? And of course, this is our angle theta. Good? So now that we've basically reduced the situation to two perpendicular field strengths, we can now use Pythagoras' theorem to find the magnitude of the resultant and, of course, a trig ratio to find the angle. So by Pythagoras' theorem, we can say that EP squared is equal to 25,200 squared plus 12,600 squared. And if you go to our calculator and we work that out, we will see that EP equal, so so 25,200 squared plus 12,600 squared, right? That gives us 7.938. So EP would be equal to the square root of 7.938 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. Right? And therefore this gives us, so square root, second function, square root, second function, answer equal. So this gives us approximately 28,174 newtons per coulomb. So the resultant field strength is 28,174 newtons per coulomb. That is the magnitude of the field strength. So because, of course, field strength is a vector quantity, we must now go ahead and find our angle, right? So this is our angle theta respect to the horizontal. So using the tangent ratio, we say that tan theta is equal to opposite over adjacent. So tan theta is equal to 12,600 divided by 25,200, which is looking like 0.5. Yeah, 0.5. So tan theta is equal to 0.5, and so theta is equal to tan inverse of 0.5. If I remember correctly, that should be about 26 point something. So second function tan 0.5, right, 26.6 degrees. So therefore theta is equal to 26.6 degrees. We could say to EPB plus EPD. So there we have the magnitude of our field strength at P and also the direction. So we could basically now state that EP, the resultant field strength at P, is equal to 28,174. I mean, yeah, we could leave it like this, but if you want to round it down to a certain number of significant figures, or even, let's say put it in standard form and to 3 significant figures. So this would be 2.82 times 10 to the 1, 2, 3, 4 newtons per coulomb at 26.6 degrees to, we could say, EPB plus EPD. And that right there is the magnitude and direction of our resultant field strength. Right? So we were able to find the magnitude and direction of the resultant field strength by first imagine placing a small positive test charge at the point P and then basically determining the direction that the charge would move with respect to each of the charges at the vertices A, B, C, and D, and that allowed us to find the respective directions of the field strengths, and we're able to find their magnitudes and find the overall field strength at P and also the direction as well. Now the next part of the question wants us to find the potential at the center of the square. Now we already found, well, not the value of r, but we found the value of r squared, and since we already found r squared, then it should be easy to find the value of r. So let's now go ahead and find the electric potential at P. Now, electric potential at a point due to a charge Q is given by V equals 1 over 4 pi epsilon naught Q over R. Now, one of the differences between electric potential and electric field strength is that electric potential is a scalar quantity, whereas electric field strength is a vector quantity. So being a scalar quantity, electric potential has no direction. Another important, another difference is that when calculating electric potential at a point due to a particular charge will take the sign of the charge. So what does this mean exactly? If the charge is positive, then the electric potential at the point due to that charge will be positive. However, if the charge is negative, for instance the charge at D, then the electric potential at that point due to that charge will be negative. So as I said, the electric potential will at a point will carry the sign. The electric potential at a point due to a particular charge will carry the sign of the charge. So essentially what we need to do is to just find electric potential at P due to the charge at A, due to the charge at B, due to the charge at C, due to the charge at D, and simply add them all up, right? So we can say that the electric potential at P is equal to electric potential at P due to A, charge at A, plus electric potential at P due to the charge at B, plus electric potential at P due to the charge at C, plus electric potential at P due to the charge at D. So the only difference that we're going to basically apply to this equation is the magnitude of the charges, because each charge, or the point rather, each charge is going to be the same distance r from the point P. So speaking about r squared is equal to 50 centimeters squared. So if we were to find the value of r, then that would mean that r is equal to square root of that. So that should be about root of 50. That's about 7.07, something around there. So r is equal to root of 50. That is basically be 5 root 2 in third. And if you want to put that so root of 2, that's 1.41. So that's basically means that r is equal to 7.0 centimeters, with the same thing as 0. So divided by 100, 0.0707 meters, right? So that is the value of r. So if you come here now and we calculate our resultant potential, if you notice, this part is going to be common for all the potentials, and so is r. So basically what this becomes is that the potential at P is equal to 1 over 4 pi epsilon naught times the charge at A plus the charge at B plus the charge at C plus the charge at D all over R. Right? And so we can go ahead now and just substitute the values. So this gives us 9 times 10 to the 9. Again, we're using 9 times 10 to the 9 for simplicity. The charge at A, now remember that when calculating potential, the potential at the point due to the particular charge will carry the sign of the charge. So the potential at P due to the charge at A will be positive, whereas the potential at P due to the charge at D and also at C will be negative. So doing that, then this becomes, so this is 5 times 10 to the minus 9. Then charge at B, that's a plus 8 times 10 to the minus 9. The charge at C is negative, that is minus 2 times 10 to the minus 9. And the charge at D is negative as well, is minus 4 times 10 to the minus 9. And that is all over R, which is 0.0707. So adding up all of that, well, this gives us 9 times 10 to the 9 times 5 plus 8 is 13. 13 minus 2, that is 11. 11 minus 4, that is 7. This is 9 times 10 to the 9 times 7 times 10 to the minus 9 all over 0.0707. So the 10 to the 9 and the 10 to the minus 9 will multiply to give 1. So therefore what remains is 9 times 7, which is 63. So this gives us 63 divided by 0.0707. And for that I will need to go to my calculator. And so we get that 63 divided by 0.0707. That gives us approximately 891. And the SI unit of electric potential is volts. So the electric potential at P is equal to 891 volts. So this is the end of the question in which we are able to calculate the resultant field strength in both magnitude and direction at P, and also the resultant, or well, not resultant, but the potential at P due to each of these charges at A, B, C, and D.